inductance. In this video, in this series of videos, we will look at inductance, and I'm going to state here what it is. Inductance, you could define it as a position of an electrical device of sorts. It could be a wire, could be a diode, but it's the opposition of I'm going to put it here, electrical device. But again, this could be a capacitor, it could be solenoid, could be a straight wire, just about anything. But though in our class we will mostly focus on a solenoid. It's the opposition of electrical device to a changing current. Key word is changing current. So before we actually before we build up to this understanding of what this definition actually means, we should recall briefly the right-hand rule. For one of the right-hand rules, there are two right-hand rules that we went over. This is one of them. We will need this right-hand rule. We will also need the Lenz's law, but maybe just with look at the picture, and then maybe quickly with one drawing. If you have a current that points, every time you have a current, every time you have a flow of charges, there's going to be a magnetic field. And if you have a straight wire like this, you could use this right-hand rule to determine the direction of the current. And so you would set up your you have to use your right hand, and then you point the thumb of your right hand in the direction of in which the current flows. Curl your fingers, and that would be the direction of the magnetic field. So something like this. Here's the magnetic field. It would be circular around the wire. And of course, if you were to move farther out, you would, somewhere out here, you would just draw another circular loop, and here another circular loop, and here another circular loop, because what's between the lines of the magnetic field? Well, more lines, since magnetic field is not really lines. Magnetic field fills up the whole space. So there's magnetic field present everywhere here, but we only draw a few select lines to indicate its shape. Okay, so keep this in mind, and now let's go ahead and consider a few things that we will need. So suppose we have a loop. Let me change the color. Suppose we have a loop, and the loop looks like this. It's just a square loop. And then let's say that somehow you set up a magnetic field, external magnetic field. Note that this loop is not connected to any battery at all. It's just 4 wires that are connected into one loop. And then let's say that we bring in a magnet, and we point the magnet into the screen such that the magnetic field of that magnet points through the loop. That points like this. Right? So there's magnetic field B that points into the loop. Now, if this magnetic field B is constant, then there is no change of flux through magnetic flux through the loop. But if this B is changing, so we're going to say now that let B increase. If that is the case, then there's going to be a change of flux, magnetic flux through the loop. And of course, change of the magnetic flux through the loop implies that there's going to be an EMF or some sort of a voltage set up in the loop, and that implies that you're going to have a current in the loop. So changing magnetic field will give you current in the loop. So let's now determine the direction of that current. We will use the Lenz's law. And so what I have here is that the magnetic field is increasing into the page. That would imply, by Lenz's law, that the current in the loop is going to oppose that, and therefore it's going to set up its own magnetic field that points outside of the loop. So for every x, I should draw a dot. And this green dot that points out of the page represents the magnetic field set up by the current. And it is set up there by the current to oppose the blue field by Lenz's law. All right, now if the green field points out of the page, then the current has to flow like this. Wait, which way? It has to flow like this. this would be the direction of the current I. And you can confirm that this is the case by using the right hand rule that I showed you here on this page. So you take the thumb of your right hand, make it point up, curl your fingers, and you'd have that the magnetic field points into the page here, curls around, comes out of the page here. Right? It points into the page here, goes under the wire, and comes out of the page here. Goes into the page here, goes under the wire, comes out of the page here. And so that works. So now I would have the current that flows in this direction, flows in this direction here, where I put these arrows. All right, let's try one more. That is maybe a reverse of this. So suppose that I have a loop that looks like this. And then let's say that I have a magnet, and I bring in a magnet, but it points in different direction. The magnetic field of this magnet, let's say, points in different direction, opposite direction. So let's say that the blue field set up now by the external magnet points out of the page like this. So this is B, the blue field that points out of the page. This is the magnetic field that I would set up with a magnet. And now let's say that I push this magnet into this towards the screen so that this magnetic field B is increasing. So I'm going to put here B is increasing. It's just that now it points out of the page. That implies that I have a changing flux through the loop. So there's going to be a changing magnetic flux through the loop, which of course gives me EMF or voltage. And if I have voltage in a loop and the loop is closed, then I'm going to get current. So if I have a changing magnetic field, I end up with a current. Now let's use the Lenz's law to determine the direction of that current. So by Lenz's law, the loop is going to oppose a change in the magnetic field. So if the magnetic field here points out of the page and it is increasing, then the loop itself is going to set up a field such that it points into the page. And it is also increasing. So I'm going to put X for every that I had before. So the green field, that's the field set up by the current. And the only way that this green field can point into the page is if the current flows in this direction. So this is the direction of the current in the loop. Right, so it would be like this and like this. All right, so the right hand rule and Lenz's law combined. Now let's see how we tie this thing into inductance. So let's move this thing up. Well, actually, let me copy something over. I'm going to copy the definition of inductance. And let's move this down. So the inductance is the opposition of some electrical thing to a changing current. Now let's see how we can get to that point. See what it actually means. Let's say we have a loop. That is, let's say we have a wire. We have a circuit with a battery. So here's let's draw a circuit here. I could put a resistor in this. It doesn't really matter. The wire itself has some resistance, so that's fine. I could put resistor in it. I don't have to. Here's a switch, and then I have a battery right here. Right now, while the switch is opened, so here's the switch. While the switch is opened, and here's a positive, here's a negative terminal. No current flows, so nothing interesting happens. But then we will close the switch, and we will consider that short period of time in which the current. So well, I drew it like this, but what we'll do is we're going to close this switch. And when we close the switch, the current will start to flow. But I want you to notice that here in this case, the current will not just flow, but it will increase. So here I will flow, but this current I will also increase. Since you start with no current and then you flip the switch, and so obviously there will be an increase in the current until eventually this current reaches some constant flow, some maximum constant flow. And so you get to this point where you have just a battery and positive negative terminal, and here's the current, but this current flows at a steady rate. Here's I, but this I is now constant. I'm going to put here constant. Right, so here the current is constant, here the current is increasing, and then here nothing interesting is happening. So we're looking at it from left to right. So this is the first sort of first stage. This switch is open. Second stage, we just closed the switch and the current is increasing. Third stage, the current has reached its maximum value and it just goes on at a constant rate. So let's draw the magnetic fields as set up by the blue current. So here there's no magnetic field, right? I'm just going to put B equals 0. There's no magnetic field through the loop. And there's no magnetic field on the outside of the loop either. Now here in this case, the current starts to flow, and so there is a current, therefore there is a magnetic field. So let's draw the magnetic field just on the inside through the loop. Well, use the right hand, point the thumb in the direction of the current, and then curl your fingers, and you will see that the magnetic field has to point. Well, it points like this. First I'm gonna draw it like this. It points out of the page here, and then into the page here, out of the page here, and then into the page here. Right, this is how the magnetic field will point. So instead of drawing all of these, all of these, and so here on this side, maybe I'll do this side as well. It would point out of the page and then into the page, out of the page, and then into the page. And of course, I would have the field set up here as well and along the top edge as well. But let's get rid of all of these and instead draw the magnetic field just pointing into the page on the inside like this. All right, so the magnetic field points into the page on the inside like this. There is a field on the outside. If I wanted to, I could put that, so the magnetic field points out of the page. But I don't need that on the outside. It's irrelevant. The field on the outside is irrelevant. I'm just going to draw the field on the inside of the loop. And this B, this magnetic field B, is also increases, because if the current increases, so does the magnetic field. And in the final stage here, you will still have the magnetic field that points into the page, but this is going to be a constant magnetic field because the current here is also constant. All right, so now we have this picture. Hopefully it makes sense. And now let's take it a little farther. So on the left-hand side here, in the first stage, before you open the switch, nothing interesting happens. So there's nothing to be added to the narrative about this circuit. Now, when it comes to this one here, though, we have an increasing current. We just closed the switch. We have an increasing current and we have an increasing magnetic field. But increasing magnetic field, well, remember Lenz's law. If there is an increasing magnetic field, so I'm going to put here, B is increasing through the loop. By Lenz's law, that implies that the loop itself is going to set up its own current I that will be current I, which will oppose that blue B. So let me do it like this. If the magnetic field here is pointing into the page and it is increasing, then the loop is going to set up its own current such that it opposes this increasing magnetic field. And so there will be a green magnetic field now that points in opposite direction. So out of the page, I'm going to put green everywhere I have this X. So here I'm going to have a green magnetic field B, which also would be increasing. And this green magnetic field will oppose the changing blue magnetic field. But that green magnetic field could be set up here only if there is a current in a wire that flows in this direction. So take the right hand, point the thumb of your right hand to the left here, curl your fingers, and you will see that the magnetic field points into the page here, but then out of the page here. This is by Lenz's law. So what I have here is, as long as the blue field is increasing, and it is increasing because the current produced by the battery is increasing, there will also be a green field set up here by the charges in the loop to oppose the increasing blue field. This is by Lenz's law. So what I have here in the middle circuit is I have two currents. There are two currents here. The blue current, which is due to the battery, and then I have the green current, which is due to the Lenz's law. And these two currents oppose. In fact, you could take it farther and you could say that the green field now is increasing through the loop. Therefore, there's going to be another set of charges that will move in opposite direction to oppose this field, and so on and so forth. If you can sort of picture how that would go, that would be there. Now, as it will happen, this green field is going to be smaller or weaker than the blue field, and so you will still end up with some positive current that flows in the direction in which the battery pushes the charges, but there will be an opposition. So the blue and the green fields, they oppose. Therefore, as long as blue current, go here, as long as I increases, there is an opposition to this increase. So the loop is opposing a change. And this is sort of the inductance. We define this opposition to the changing current as inductance, right? Look at the definition here. Inductance is the opposition of electrical device to a changing current. In this case, the device is just a wire. Now let's consider the third stage. So here what we have is that the current I is constant. The current has flown for long enough, and the battery has pushed the charges for long enough, where we have achieved a sort of a steady state in the sense that the current is not changing anymore. So there's a constant current, therefore the magnetic field is constant. And if the magnetic field through the loop is constant, then the loop will not oppose it because there is nothing to oppose. Since if anything, by Lenz's law, the loop would oppose a changing flux, or changing magnetic field would oppose a change. So nothing interesting is happening here anymore. Nothing interesting was happening there in the beginning, but while the blue current was increasing, the loop opposed that change, setting up an opposite current that points in opposite direction. All right, and that process of opposing the changing current is what we define as the inductance. Let's do one more example of this. So suppose you have a loop, and this loop is connected to the battery, but here's the first stage where the switch is open. So the switch is open, nothing is happening here, no flow. It's the first stage. And then the second stage is, but you know what? Let's, what we want to do is we want to change this a little. Otherwise it'd be the same, really the same story. Why do that twice? So let me flip the battery. Let's do it like that. And now here's your switch. Right, so the battery points in opposite direction. This will make you visualize the same thing, but in a different way, and that's always a good thing. And then we take this switch, we close the switch. So here's the battery. It points in this direction. Here's the switch. We close the switch, and suddenly now what happens is the current starts to flow, but the current flows in this direction. So the current flows now like this, and it's increasing. Right, so this current is increases, and until eventually it reaches its maximum value. That doesn't take long, but it gets there in some time. It's not instantaneous. And so eventually this current flows at a constant rate, its maximum flow rate. So here you would have I is constant, and then here in current I. All right, so on the left hand side there is no magnetic field because there is no current flowing yet. Here you have a magnetic field. In the middle circuit you have a magnetic field, and here you also have a magnetic field produced by the current due to the battery. Let's determine its direction. So take the right hand, point the thumb of your right hand up, curl your fingers, and you will see that the magnetic field would do something like this. Out of the loop and into the page on the outside, and here it would point out of the loop and into the page on the outside. So I'm only interested in the magnetic field on the inside. So instead of drawing these half circles, I'm going to simply draw the dots to indicate that the magnetic field is coming out of the page here. So here's B, and it is increasing, right? B field here is increasing because the current is increasing. Now, if the magnetic field B through this loop is increasing, then the loop will oppose that change by Lenz's law. And so the loop will set up its own magnetic field that points in opposite direction and opposes that increase. So it points in this direction. I'm going to put X's everywhere I have it at. There's going to be a green field that opposes the change, and that field can point in this specific direction only if the current in the loop flows, let's see which way, this way, flows in this direction. And of course what we see here is that the green current opposes the blue current. And so now what we get here, that for as long as the blue current is increasing, we will get the green current present. So we have I, blue I, we have green I, and then the two of both of these oppose. They oppose, and that's that. The very fact that the loop will oppose change in the current, that is the property that we will define as the inductance of this loop. Now, when you go to the third picture here, third stage, in this case, the magnetic field due to the blue current set up by the battery still points out of the page. But this magnetic field is constant now. It's reached its maximum value. And since this B field is constant, there's nothing to oppose here. So that the picture ends with the blue field being constant pointing out of the page. So go back to the definition of the inductance. The inductance here is the opposition of an electrical device to a changing current. Now I'm going to add something to it. So suppose that instead of a single loop, right, a single loop will have certain opposition, will amount to a certain opposition that we can quantify to the changing current. But suppose that instead of a single loop, you have, so here's the loop, right? Suppose that instead of a single loop, and you now have, a bunch of loops. Yeah, that's not good. So let's, what I'm looking for is a solenoid. So let's say that you have a battery here that looks like this, and then plus minus, and the current flows into this, and then it starts to curl around, and the wire curls around, we end up with a solenoid, and then that last one does something like this and comes back. All right, so we have a solenoid which has a bunch of loops right now. Which one of the two? A single loop? So let's now draw a single loop here. Yeah, that's about right. Can work with this. It's a plus minus. Ooh. Anyways, here you have one loop. Kind of have two loops. See the little one here. But anyways, here you have one loop, and here you have a bunch of loops, and I can, add as many as I wish. I could have thousands of loops if I want to have here. So which one of the two will have a greater opposition to a changing current? A solenoid with multiple loops, or just a single loop here? Well, obviously it would be this one. There are many more loops here that will set up their opposition to the changing current than just a single loop here. And so really what we are after is, for many practical purposes, the solenoids are called inductors, because they will have a significant inductance, meaning they will have a significant opposition to a changing current. Now, a single loop will also have inductance, or will have opposition to the changing current. It's just that its inductance is going to be rather insignificant. However, in some applications, you may have to consider inductances of even straight wires, as long as they're within a circuit, closed circuit. But anyway, so now we have conceptual framework for what inductance is, and the next thing is to try to come up with some sort of an expression where we can quantify this thing. Let's go back to the definition. So here, inductance, opposition to an electrical device, of an electrical device to changing current.